Well, good evening, everyone. Thank you for attending this short webinar on dynamic analysis in RAM series. And, well, my name is Daniel Sa, and I will be presenting the different aspects of the DynSol module of RAM series through two simple examples. And so, first of all, allow me to introduce this webinar agenda. First, just a very brief introduction to CompassIS software. And then also a quick overview on RAM series features and applications. And finally, two examples of dynamic analysis in RAM series. Both of them can be found among the validation cases of RAM series in our webpage. So, of course, any questions or comments that you may have, you can send them to my mail. Okay, so let's introduce a little bit CompassIS software. Well, the main solver modules are gathered in a main simulation suite, which is integrated in a single graphic user interface. This interface integrates geometry and data definition, as well as mesh generation and post-processing. The solvers included in the suite are Tdyne CFD, which you may already know, which is for fluid dynamics, heat transfer, and multiphysics analysis. Also CFM for seakeeping and maneuvering analysis. And finally, RAM series, which is the deal for today. So about RAM series, it's the module for advanced 3D structural analysis based on the finite element method and including non-linearities like geometrical, nonlinear materials, and nonlinear boundary conditions. Different types of elements as beams, shells, solid cables, and membranes are included, so almost any kind of problem can be solved. As a result of the integration of Tdyne, of the module RAM series in Tdyne, coupled analysis with fluid dynamic and seakeeping solvers may be performed. So fluid structure iteration is, of course, available. Regarding the technical features, of course, linear static analysis is available, and dynamic, which englobes model, frequency domain analysis, and that direct time integration, which is what we are going to see today. And also element-to-element contact impact algorithms are available. And as I mentioned before, nonlinear solvers for large displacement. Apart from all the mentioned, as you can see, we can also perform fatigue and buckling assessment. A large database of metallic profiles is available. Composite laminate shells and beams are also available. And I think it's time enough to begin with the examples. So regarding the first example, it's so-called flying spaghetti, which involves nonlinear dynamics. This is a numerical example extracted from an article in the American Society of Mechanical Engineering journal. The article is called On the Dynamics of Flexible Beams Under Large Overall Motions by G.C. Simon. This example is also included as a validation case for RAM series, which you can find in our webpage. So, go directly to the example. And, well, it's representing a flexible rod with free ends, so no constraints at all. And initially placed in an inclined position, as can be seen. The properties of the flexible rod are already inserted in the graphic user interface and assigned to the element. Of course, these properties are the ones appearing in the article. So first, the mechanical properties are assigned So the area of the section, the Young modulus, shear modulus, specific weight, and so on. And of course, the inertia properties for we are dealing with a dynamic analysis. So in this case, they are also applied to the whole geometry, to the line in this case. And they are representing the inertia moments of the flexible rod. So regarding the analysis configuration, of course, this structural analysis, you can see in the same interface, you could choose to perform any other of the analysis, fluid dynamics or sea-keeping, thermomechanical analysis, or fluid structure interaction analysis. In this case, of course, structural analysis is in meters, international system, and the gravity is in the y direction. Regarding the type of analysis being performed, as I mentioned, is a dynamic analysis, and we will be dealing with nonlinear geometric solvers. And regarding the dynamic solver aspects of the simulation, yes, it's a direct integration with a total physical time of 10 seconds and 0.1 second time step. Regarding the integration method, an implicit energy conserving algorithm is chosen in this case. So among the others, there are a few more, but following the article, energy conserving algorithm will be used in this case. So regarding the loads, in this case, force and torque are applied simultaneously at one of the ends, the bottom end of the rod. So you can see this is a dynamic load applied to this end of the line, the moment and a force with certain values, and the force and the moment are removed at the same time at t equal to 2.5 seconds, and consequently a free flight will occur immediately after. So if you check the time history of this load, we can see that that's exactly what is happening. So the load is applied only the first 2.5 seconds and then is removed. So there is not very much more regarding the configuration of the analysis. Just to mention the mesh that has been used, just 21 nodes and 20 linear elements, which you can check in utilities status. You can see the number of nodes and elements. Also, they can be labeled. If you choose to draw the mesh, you can label all the elements so as to visualize them. Okay, so this is quite a quick analysis. The actual calculation takes about 4 seconds. You also can check it here in the process info. See the convergence, which is output at each time step, and the total time needed for solving this analysis. And of course, we can proceed directly to the post-process and see the results. So among the results that can be seen in the post-process, of course, it's interesting to see the displacement of the bar, and we are going to draw it so it can be visualized a little bit better. And of course, we can perform an animation of the form of the flexible rod, so as to see the free flight of the so-called flying spaghetti. So let's draw the deformed and visualize an animation of the whole process when the force and moment are removed. So in this moment, the free flight of the spaghetti starts, and the nonlinear solver does its work and solves the problem. And of course, there's an issue of energy which needs to be conserved, and that's another result that can be visualized. In the total energy, which we can check, for example, in the bottom of the bar. So we will just check, look for that point, select it, and after selecting the energy result, we can plot time graph of this result. So let's select the point and plot the correct time graph. As you can see, the first 2.5 seconds, the energy is growing until the force and moment are removed, and then the rod is released and flying away and conserving the energy. So, okay, also for example, the angular momentum or the linear momentum are conserved. That's a result that can also be plotted. You can see here the angular momentum in any point. We can also obtain the time graph for this result. So, well, I think it's pretty clear. This analysis, as I said, is in the validation cases in our web page. You can send all the question you have, and we can go through the next example, which is a cable network. It's also a dynamic analysis, of course, and deals with cable elements. It's just a cable network, and it's also from an article from the Final Elements in Analysis and Design journal, and the article is called Nonlinear Static and Dynamic Analysis of Cable Structures. Some Korean authors called Kim Seon-yeok. Of course, this model, we have also used it for validation, so you can find it in our web page in the corresponding section. So while it gets loaded, I will just explain a little bit this model. It's just an example consisting of a plain cable net, which is subjected to both static and dynamic loads. And of course, the dynamic load in this case corresponds to an earthquake loading, which is applied in the vertical direction of the structure. But let me show you this. Let's see first the cable network. You can see the geometry. there are constraints in this case, so the network is fixed in the points, the extremal points. And in this case, the material, well, the element is a cable. There are two different cable sections defined, and the only difference between both of them is the pre-stressing of the element. So you can see that all the linear elements have been assigned with the cable properties, and you can see the properties, both of them, the area, the mechanical properties, and the pre-stressing. So it's slightly different for both of them. And regarding the loads, as you can see in this case, as I mentioned, there are both static loads, 4 punctual loads in the central points. You can see they are applied in those points. Some punctual weights. Also, the self-weight of the structure is used in this case. And of course, the important load in this case, which is the time depending load corresponding to the earthquake. In this case, this is interesting because it's not applied as a usual load, but applied to the whole of the structure as a ground acceleration. And the exact signal of the real earthquake, which was measured, is applied to the structure. So it's a vertical acceleration with the following time history. As you can see, there's the first part where no load is applied, no dynamic load, so just the static, the punctual loads and the weights will be acting. And then the dynamic loading will start. So we will be able to visualize this in the post-process. So what else? Of course, there's the dynamic masses corresponding to these points. This is something that the article in which is based this example also includes, so why not include it? And well, the analysis is very much the same as the previous one. It's configured as a dynamic analysis with nonlinear geometry. We are using cable elements and probably large displacements. And in this case, total physical time of 74 seconds is analyzed. So this means 3,700 steps of 0.02 seconds of time a step. And it doesn't take too much time. As you can see, it's about 7 seconds to analyze all the physical time. So just quite quick actually. And regarding the mesh, it's also a very simple mesh. It's just about 84 nodes and 84 elements. We can also label them. I can show you the elements and the nodes. In this case, as I was guessing, yes, so 84 elements. So it's a very simple analysis. Doesn't take much CPU or memory. So we can go directly to the post-process and visualize some results. Of course, among the results, interesting ones, I think, are the dynamic response, which can be plotted for any point of the structure, or just simply create an animation of the process. You can see the displacements, and in this case I'm going to use a factor of 10 for the deformation so as to visualize it a little bit better. And we can perform an animation. So you will see that the first stage of the animation is just the static loads acting, so it will deform and keep that position until the actual dynamic. Well, let me draw the original also so you can see how it's getting deformed. And as I was saying, after some time the earthquake starts to take place and all the structures vibrate with the time history signal. So for the moment, just a static load, and after some 20 or 30 seconds the earthquake starts to take place. So there it goes. Depending on the refreshing of the internet connection, you will see it earlier or later, but now it's already moving. And of course, it's the response of the cable network to the earthquake. This signal can be plotted. So, for example, we stop the animation and make a plot of one of the movement of one of the points. Let's take one of these connection points, if I can, yeah, and get the time graph of the displacement. You will see that follows the signal of the earthquake load. You can see here the response and the displacement of one of the connection nodes of the cable network, and so on. Well, there are some other results. Of course, the axial force can be visualized, or the reactions on the constraints. These are natural results. And well, hope this was of any help and you enjoyed it. And of course, if you have any comments, any further information request, please don't hesitate to contact me, mail. And well, nothing else. Thank you for your attention and hope to see you again. Bye-bye.